All right, today we are starting Chapter 8, which is Bonding Part 1. So want to guess what Chapter 9 is? Good, Bonding Part 2. So next test will be just Chapters 8 and 9, so it'll be Bonding Part 2. So the beginning of this, we will talk about the general idea of Lewis structures. There's different theories of bondings, how things bond, and why things bond. We will start with this simplest theory, which is Lewis theory, and then we'll build up to the more complicated theories in Chapter 9. And we'll also briefly talk about the difference between ionic bonding and covalent bonding, which in Chapter 2, we didn't really talk about the difference in bonding, just how to recognize if something's ionic or covalent. Qualitatively, today we'll talk about how to do it quantitatively, so how to numerically determine if a bond is going to be ionic versus covalent. So, first thing we're going to talk about is Lewis dot symbols. So in Chapter 7, we learned that the most important electrons in an atom are the valence electrons, or those in the outermost shell. And we learned that the reason why these are the most important is because they're the ones involved in bonding. So before we talk about bonding theories, we need to talk about those valence electrons. We also learned in Chapter 7 that about the octet rule, the idea that everything wants to have the same number of electrons as a noble gas. But in Chapter 7, we just use this to make ions. They're only going to gain or lose electrons in order to look like a noble gas or be isoelectronic with a noble gas. So a Lewis dot symbol is a way of shorthand showing that element and its number of valence electrons using dots. This can quickly show us how close it is to having an octet or being isoelectronic with a noble gas, and also show us things like how many sites it has available for bonding if it's going to covalently bond, or how many electrons it has to gain or lose if it's going to become an ion. So the general idea is it's just going to be the atom with the number of dots around it representing the number of valence electrons. So, for example, we know everything here in group 1, let me get my laser pointer here. Everything here in group 1 all has one valence electron, so they're all going to have one dot. Everything in group 2 has two valence electrons, so it will have two dots. Notice we didn't put them on the same sides. Rules from Chapter 6 on orbital diagrams kind of apply here. One of those rules was that electrons hate each other, so they're not going to pair up unless they have to. So we're going to follow that same kind of rule, but now we're going to have 4 different sides to our element. So for example, everything in group 4 over here has 4 dots, so it's going to be 1 per side before we get to 5 dots and we start pairing up. Now it does not matter when you draw these which side you pair up first, as long as you have at least 1 dot per side before you pair them up. All the way to over here, the noble gases except for helium all have 8 valence electrons, that's 2 per side, and it has a fully filled valence shell. So those are the electron or Lewis dot structures for the neutral atoms, and this is on page 327. So to show it for an ion, we're just going to add or remove however many dots that corresponds to however many electrons we've added or removed. So let's try this out. The question says, write the Lewis dot symbol for the fluoride ion, the potassium ion, and the sulfide ion. So we're going to, just like we did with electron configuration, start by drawing the Lewis dot structure of the original atom and then alter it to account for the ions. Let's do fluoride first. So fluorine is in which group? 7. So it has how many dots around it? 7. So I'm going to do 1 per side. 1, 2, 3, 4, 5, 6, 7. So now it has 7 dots around it. To become fluoride with the negative charge, are we adding an electron or losing one? Adding one. So we're just going to add one more. There's only one spot available, so it's going to go right there. Then we're going to put this in brackets and put a charge on the outside to show it's charged. The reason why with negative ions we put brackets is to show that that charge is on the overall atom, not just on one of those little dots. So there's the Lewis dot structure for the fluoride ion. Potassium, K plus. So the original atom for potassium has how many dots? 1. So to become potassium plus, what is it going to do? Subtract it. So I'm going to erase that dot, and then I'm going to give it a positive charge. We don't need brackets on positive charge ions because they shouldn't have any dots, so the only thing there is the symbol. So we know it's the symbol that got the charge. So the Lewis dot symbol for potassium plus is just a K plus because there's no dots. All right, sulfide. So sulfur is in which group? 6. Good. So we're going to have 6 dots. 1, 2, 3, 4, 5, 6. Generally, when you have group 6, you usually put the two sides that are paired up opposite from each other. Doesn't really matter if you put them side to side or top to bottom. But just again, electrons hate each other, so they're going to try and spread out. So sulfide 2 minus, what am I going to change? Add 2. So I'm going to add 1 there and 1 there. So now I have a fully filled octet. And again, put it in brackets and put the charge on the outside. And there's the Lewis dot symbol for sulfide. Not so bad. So any questions about how to draw the Lewis dot symbol for an element or a monatomic ion? Do you remember what I mean by monatomic? What does monatomic ion mean? Not polyatomic. It means the ion is made of how many atoms? 1, right? So these are all monatomic ions because they're ions, but they only have 1 atom. All right. Moving on to section 2. So section 2, we're going to talk about ionic bonding, and we're going to talk about lattice energy and the Born-Haber cycle, which is the way we calculate the lattice energy or measure how strong an ionic bond is. So one of the big parts of all of these bonding theories is not just how things bond, but we're trying to figure out why things bond. So ionic bonding, we already know briefly from chapter 2, means I have 2 ions of opposite charge. One's positive, one's negative. Generally, the positive one's a metal and the negative one's a nonmetal. And because they're oppositely charged, they're going to be attracted to one another. So they're going to stick together and form an ionic bond. So, for example, if I had potassium and iodine, and I were to draw the Lewis dot structure symbols for potassium and iodine, potassium's in group 1, so it has 1 dot. Iodine is in group 7, so it would have 7 dots. 1, 2, 3, 4, 5, 6, 7, like that. When they come close to each other, they both have something they want. Potassium has 1 electron. It doesn't want that electron. It wants to give it away. Iodine has 7. It wants to gain 1 more. So what's going to happen is an electron transfer. Change colors here. So this electron will get transferred over here, like that. Now, once we have that transfer, now we have the 2 ions as charged particles here. So the potassium is going to lose an electron. The iodine is going to gain that electron. So when you add them together, these electrons will cancel. So we'll have the 2 neutral atoms come together, and then we end up with 2 ions. Now we studied the energy associated with this back in chapter 7. So the energy associated with losing an electron back in chapter 7, that was the ionization energy. So IE1, because it's the first one. Sorry, got that backwards. That's gaining the electron. Ooh. So gaining the electron is the electron affinity. And down here, I'm losing electrons, so that's the ionization energy. Like that. So from chapter 7, the ionization energy for potassium is 419, so that was from the table of ionization energies. And the electron affinity of iodine is negative 295 kilojoules. What does the fact that it's negative mean about that energy? Is it gaining or losing? If I'm having negative energy, am I losing energy or gaining it? No, if I'm negative, I'm losing it. So it's releasing that energy. So this is energy being released, while this one that's positive is energy being gained. What was the terms for that back in chapter 5? A reaction that gains energy is a what reaction? Good, endothermic. While an energy that releases energy, or a reaction that releases energy is good, exothermic. So if I add these 2 processes together, I end up getting a net of 124 kilojoules of energy that's positive, meaning overall the reaction should require energy in endothermic. Therefore, if I had this reaction happening, the reaction vessel would feel what? Hot or cold? If you had this reaction going on in a vessel and you're holding it in your hand, would it feel hot or cold? If it's gaining energy from its surroundings, will your hand start feeling hot or cold? Cold, because it's pulling heat out of your hand, right? So that's what we would expect. But in reality, forming ionic bonds is extremely exothermic, meaning when this reaction actually happens, what we observe is that a huge amount of heat is released in the formation of this. So to quantify this, we need to consider a different kind of energy. This is called the lattice energy. The lattice energy is the energy associated with forming ionic bonds, or in reverse, breaking them. Because as we know, if you reverse any reaction, you just change the sign of it. So the lattice energy, to make it positive or requiring energy, would be the amount of energy it takes to break an ionic bond and be left with the two separate ions in their separate gas states. So for example, the process of vector potassium iodide, if I started with the ionic compound and broke it apart into the two separate ions in the gas phases, the lattice energy for this would be the amount of energy it takes to run this process. So for this particular example, it's 632 kilojoules, or that's how much energy it would take to break the lattice bond, or break the ionic bond. The higher the lattice energy, the more energy it requires, therefore the stronger or more stable the ionic bond. So bigger lattice energies mean stronger ionic bonds. Because it takes more energy to break it. Stronger ionic bonds. Apparently the screen needs to be cleaned because it keeps on making those little horizontal lines. They're fun. All right. So this table, which is on page 328 of the 5th edition, shows you just comparing different compounds and their lattice energies. Of course, most of the questions I ask you that are going to compare are not going to be one of these, so you still have to know the idea behind it, but this is just showing you some examples so we can try to figure out what kinds of things affect lattice energy. So in chapter 5, what was the energy that we had between charged particles called? The what energy? It was the very first energy we talked about in chapter 5, our very first equation in chapter 5.
Kinetic?
Close, that's the energy of movement. But close, it is a kind of potential. What does the EL stand for? Electrostatic, good. Electrostatic energy. So the first equation we had was electrostatic energy is not equal to, but proportional to Q1, which is the charge of the first thing, times Q2, which is the charge of the second thing, divided by the distance. So that was the equation we had back in chapter 2. So in an ionic bond, the energy between the ions is the electrostatic energy. Therefore, that's the energy that has to be overcome. In this chapter, they talk about it in terms of force instead of energy, but it's the same general thing. So the equation for the force between charged particles is proportional to, looks almost exactly the same, Q1 times Q2 divided by the distance, but we're going to square the distance. That's the only thing difference. But when you're just comparing two things, it doesn't really matter if you square the distance for both or not. It'll give you the same answer. This equation right here for the force between charged particles is called Coulomb's law. Coulomb's law. Named after the same scientist that gave name to Coulomb, which is the SI unit for charge, which we'll see again in another section or two here.
And what was that equation?
This is showing you the force between charged particles. Therefore, that's the force that has to be overcome in order to break an ionic bond. So the bigger this force, the bigger the force between the particles, what would you expect about the lattice energy, which is the energy that it takes to break it? Would it be higher or smaller if the force gets bigger? Higher. Good. So bigger force means the lattice energy would get bigger. Put that up here. Bigger force of attraction would yield a bigger lattice energy. So the most important takeaway from that is the charges on top, Q1 times Q2. So the charges are just going to be the charges on our ions. So if I have bigger charges, so +2 and -2 versus +1 and -1, what will happen to my force? Will it get bigger or smaller if I make the charges bigger? If I make Q1 and Q2 bigger, will my force get bigger or smaller? Bigger, right? If I make the numerator of a fraction bigger, then the overall number gets bigger. So bigger charges equals a bigger force. Looking at this table, everything in this first family, or this first row here, these are all +1, -1s. Lithium, sodium, bromine, iodine, etc. These are all +1, -1s. Over here, though, magnesium here has a 2+. Over here, oxygen has a 2-. So we're getting to bigger charges. What happened to our lattice energies here? Did they get much bigger compared to this stuff? Yes, they got much bigger. They got much bigger because the charges are bigger. Now down here, magnesium oxide, both of them are 2. Magnesium is 2+, oxygen is 2-, and at its lattice energy, even bigger. So bigger charges equals bigger lattice energies. Skip ahead 2 slides to show you that. Here's lithium fluoride versus magnesium oxide. Comparing Coulomb's law for both of them. So there's Coulomb's law. Lithium fluoride and magnesium oxide, both of them are going to have pretty similar bond lengths. So that's going to be the distance in the bottom here, are pretty close to the same thing. So the main thing we're comparing here is the charges. And we find that it is almost a factor of 4 times bigger for the magnesium oxide versus the lithium fluoride. And sure enough, your lattice energy for magnesium oxide is almost 4 times bigger. So the most important thing when comparing lattice energies is the charges. If the charges are different, bigger charges will give you bigger lattice energies. So what if the charges aren't different? So how do I tell the difference between these guys? Why is lithium fluoride bigger lattice energy than lithium chloride? Both of them have the same charges, so what about Coulomb's law must be different for the two of those?
The distance?
The distance, good. So the distance in any ionic bond, so here's our lithium iodide here. The distance in any ionic bond is going to be the sum of the ionic radius of each of the ions. So have we learned about ionic radii yet? Did you just take a test that had the questions about ionic radii? Yes,
but
yes.
Did we learn how to calculate the radius, just
no.
comparing it?
We just learned how to compare it.
Okay.
Yeah, we just learned how to compare it, but we did have a table of ionic radii. So in Chapter 7, we did have a table of ionic radii. Now, when you're looking at this, that's where these numbers came from here. These numbers come from that table back in Chapter 7 of ionic radii. The unit is different, though. So, for example, lithium. Lithium, it says 0.76, and it has an A with a little thing over that. If I look back at Chapter 7's table, what it has for lithium plus in Chapter 7 is it says the ionic radius is 76 pms. What does the prefix P stand for? What is that? Pico, right? Pico means 10 to the negative 12, or 1 picometer is 10 to the negative 12 meters, so 1,000 times smaller than a nanometer. This little funny looking A here is called an angstrom. An angstrom is 10 to the negative 10 meters, so when we're comparing that to picometers, it is 100 times bigger than a picometer. So that's how we went from 76 picometers to 0.76 angstroms. It came from the same table, they just changed the unit. So, divided by 100. I'm pointing that out because in 2 sections we're going to have some unit conversions that requires to go between meters, picometers, and angstroms. So introducing that idea of those different units, where they came from. Now we have that table, so that's good and handy, but what if you don't have the table? Can we still tell which ions are going to be bigger? So comparing these 3 ionic compounds, they all have iodide ion, so what we're really comparing here is the cation. So our cations are lithium, sodium, and potassium. Just looking at the periodic table, lithium, sodium, and potassium, how could we tell from the periodic table that of these 3, lithium should be the smallest? Just looking at the periodic table, how could you tell? Perfect. As you go down a family, the radius gets bigger because each time you go down a row, what are you adding? A shell. You're adding a whole nother shell. So just looking at the periodic table, we know potassium should be the biggest and lithium should be the smallest. So if the question is just what is the biggest, which of these 3 has the biggest lattice energy and which has the smallest, they all have the same charges. What we're looking at is the distance. And since they all have iodine, we're looking at the radius of the cation in this case. So the bigger the radius, the bigger the distance. Picture magnets, think of the force between them. The further away the magnets are, what happens to the force of attraction I feel between them? It decreases. So that's Coulomb's law. Good play. So as we increase the size of our ionic radius, our distance here will increase, therefore our lattice will get smaller. So when the charges are the same, the bigger ionic radius equals a smaller lattice energy.
Did you write that down?
Yep.
Thank you.
I'll make that disclaimer also because the charges are more important. If the charges are different, then that whole thing goes away. So when charges are the same, bigger ionic radius equals smaller lattice energy. When the charges are different, then whichever one has the bigger charge has the bigger lattice energy. Ready to try this out?
Yes, ma'am.
All right, so this is sample problem 8.2. Arrange magnesium oxide, calcium oxide, and strontium oxide in order of increasing lattice energy. So we have a table of the lattice energies, but although magnesium oxide is on that table, strontium oxide and calcium oxide were not on the table. So we're going to have to use Coulomb's law to determine which ones would be the biggest and which one will be the smallest. So we're saying increasing lattice energy, so that means we're going from the smallest lattice energy to the biggest. Smallest to the biggest. So the first thing we need to check between these 3 things is whether or not the charges are the same. Magnesium oxide, calcium oxide, and strontium oxide. Are the charges the same for all 3 of those? What's the charge on a magnesium ion? Good. 2+. What's the charge on a calcium atom? 2+. Strontium? 2+, because hey, they're in the same family. So are the charges the same for all 3 of these? Yes, so if the charges are the same, what are we now comparing?
Ionic radius.
The ionic radius. So these all have oxygen, so what we're really comparing is magnesium versus calcium versus strontium. So let's look at ionic radius. So the smallest ionic radius to the biggest. And then down here we're going to do lattice energy. So between magnesium, calcium, and strontium, who should be the smallest radius? Good, magnesium, because he's the highest in the family of those three. So magnesium. Then who should be the biggest? Strontium. Good, with calcium in the middle. 2 plus, 2 plus, 2 plus. All right. So for the lattice energy, good, it's the other way around, because the smallest ionic radius should have the what lattice energy? Biggest. Therefore, magnesium oxide should be the biggest lattice energy, and who should be the smallest lattice energy? Strontium oxide. With calcium oxide in the middle, still. Like that. So this is very helpful because you can calculate the lattice energy, which is what we'll go over next, but it's a lot of steps. And so I've seen a lot of students get a question like this in the test, and they sit there and they calculate the lattice energy of all three of them. Calculating the lattice energy is a 5-step process. So you'd have to do it 5 steps times 3 compounds. That's a lot of calculations when this was a whole lot faster. So if I'm just asking you to compare which one's bigger or put in order of increasing, use Coulomb's law and the idea of the charges or the distance. Do not go through calculating the lattice energy if all it's asking you to do is compare. So any questions about that before we go into actually how to calculate it? So how to actually calculate the lattice energy is a process called the Born-Haber cycle. So I've got it shown here in white, but in your textbook, we've got a nice 2-page spread, got it in full color, a little bit easier to follow, and they've also color-coded each step, so you can keep track of which step. Are you on the blue step or the green step, etc. But on the PowerPoint slides here, I just have it in black and white. So again, lattice energy is how much energy it takes to go from the solid compound all the way to the 2 separate ions in gas phase. We're going to have 5 steps to get there. So step number 1 is going to be taking this solid compound and breaking it apart into its 2 separate elements. To figure out how much energy is associated with that, we go back to chapter 5. The reverse process, going from the 2 elements in their natural states into the compound. What do we call the energy associated with forming a compound from its elements in their standard states? The enthalpy of what? Formation. Good. So in chapter 5, we had the enthalpies of formation. Where do we find those enthalpies of formation? Good, in the back of the book in the appendix. So the enthalpy of formation right there from the appendix is the energy associated with that process. But I made it negative, or I switched the sign. The reason I switched the sign is because this is the enthalpy of formation, going from the elements to the compound. So if I'm going backwards, when you reverse a product process, what do you do with this enthalpy? Reverse the sign. So that's why it's got a negative in front. So that's the enthalpy of formation from the appendix, reversing the sign. So that's the first step. We've broken apart into the 2 separate elements. Next step is we need to go from the natural state of chlorine is Cl2 gas, right? But we want just to be 1 atom. Same thing with sodium. Natural state for sodium is a solid, but we need it to be a gas. So step number 2 is we're going to do the cation first. Doesn't really matter which one you do first, but we'll do the cation first. To go from our metal as a solid to our metal as a gas. Now, because the natural state of a metal, except for mercury, is a solid, the process of going from the solid to the gas is going to be the reverse of the enthalpy of formation. Or sorry, it's going to be the enthalpy of formation, but not in reverse, because now we're going from its natural state to something that's not its natural state. So step 2 is going to be the standard enthalpy of formation for that metal in the gas phase. And again, you can find that in Appendix 2. Step 3, we're going to take our nonmetal and we're going to make it a single atom in the gas phase. So we're already in the gas phase, that's okay. But natural states for most of these nonmetals are diatomics. We need just 1 atom. So the next step is the standard enthalpy of formation to just make it 1 atom. So again, all 3 of these values can be found in your appendix. Standard enthalpy of formation of your compound, standard enthalpy of formation of your metal but in the gas phase, and the standard enthalpy of formation of your nonmetal but as a single atom. So those first three values come from the appendix. So 3 steps down, 2 to go. Now at the end of this step, we have our 2 elements. We have them separate. We have them in the gas phase. But lattice energy is how much energy it takes to break them into their ions. So the last 2 steps are making those into ions. So step 4, we're going to do the metal into an ion. So the energy associated with pulling off an electron and making a positive ion is the ionization energy. Where do we find ionization energies? There's a table. Where's the table for ionization energies? Close, not 6, but 7. Good. So chapter 7 has a table of ionization energies. Now to make chlorine into the negative ion, that's electron affinity. Again, that's chapter 7. The reason why we have a negative in front is because electron affinity is energy being released. So we need to make it negative to show that this is exothermic, it's releasing that energy. So there's your 5 steps. Step 1 is the opposite of the enthalpy of formation of your compound. Step 2 is the enthalpy of formation of your metal in the gas phase. Step 3 is the enthalpy of formation of a single atom for your nonmetal. Step 4 is the ionization energy of your metal. And step 5 is the opposite of the electron affinity of your nonmetal. So those are your 5 steps. As you can see, once you've got all of these, we can use Hess's law. We're not rearranging anything, just we use Hess's law that says when you add reactions together, you add their enthalpies. So we pull all of those values. I don't think it's on the slide here. Oh, there's this. We pull all those values and we just add them together. I don't think they had the actual values for some reason. But if you're following along in the textbook on that 2-page spread on page 332, 333, it gave what all of these values were. So, and it also color-coded it so you knew which value came from which step. And they're in order, right there. So not so bad, we're just adding 5 numbers. The tedious part is looking at the tables for those 5 numbers. So for that reason, I want you to know how the Born-Haber cycle works. I'm not going to actually ask you on a test or even a homework question to actually do the Born-Haber cycle because it's just basically tedious looking up all the values. Learn Smart, of course, might ask you because Learn Smart's an algorithmic program and it'll throw things at you that it thinks you're ready for, but I will not ask you on a homework or a test to actually calculate it. You just need to know the general idea of the Born-Haber cycle. So any questions about those 5 steps?
Could you go back so I could take a picture of that?
Yep. Sorry, I kind of made it messy. But again, it's also on the 2-page spread on page 332. A little bit prettier.
No, I actually followed what you did pretty well.
Good.
It's actually crazy if I just sit and pay attention to what you're doing rather than trying to copy everything down. It actually clicks and makes sense.
Good. Yeah.
So,
That's why I always post the PowerPoints, so you don't have to worry about copying down every word I say.
yeah, I forgot to print them off this morning.
Some people learn better from copying down everything, and other people learn better from having that already there so they can listen. Best really is to do both. Listen during the lecture, and then afterwards write down what you learned in the lecture before you forget it all. All right. So I'm going to skip over this next sample problem because it's just tedious. It's find the lattice energy of this is cesium chloride, and again, it's just looking up all these values. So these 2 were from chapter 7, and then these 3 were from appendix 2. So you figure out which ones should be left as is and which ones you need to reverse the sign of and add them together. That's all there is to that. So we are done with ionic bonds. Woo! For the rest of chapter 8 and chapter 9, we're just going to focus on those covalent bonds. So the first main theory of bonding we're going to talk about is the Lewis theory of bonding. The reason why we focus on this is because it is the simplest and easiest theory. There's a lot it doesn't explain, but because it's so simple and easiest, this is the most common one that chemists will use when they're just showing a compound. They'll show the Lewis structure for it because it's simple and easy to understand. So the idea of this is that in a covalent bond, electrons, instead of being transferred like they do in an ionic bond, are going to be shared. So a covalent bond is the sharing of electrons. So same idea happens here. They both want something, but now instead of transferring electrons, they are going to share the electrons so that both of them end up feeling like they're isoelectronic with a noble gas. So for example, let's look at our simplest, smallest covalent molecule, which is the diatomic homonuclear molecule hydrogen H2. So each hydrogen's Lewis dot structure has one electron. What noble gas does hydrogen want to be isoelectronic with? It's the nearest one to him. Helium, good. How many electrons does helium have? Two. Therefore, hydrogen wants to have 2 electrons. So this hydrogen isn't very happy with 1 electron. He wants another electron. So he sees this other electron over here, and he's going to reach out and he's going to grab it. But meanwhile, what's that other hydrogen doing? Is he just going to give up his hydrogen? No. Yeah, he's going to look over here and go, hey, you got an electron. I want that. So he's going to reach over and grab that. And they're going to pull. And both of them are going to pull and pull and pull until the distance between them decreases, and you end up with this, where the pair of electrons are being shared between the 2 of them. So with the pair of electrons being shared between the 2 of them, both hydrogen atoms now feel like they have 2 electrons. And so both of them now feel happy. I've got 2 electrons. I look like helium. I'm nice and stable and cool because I'm looking like a noble gas. Generally, in Lewis dot structures, we draw the shared pair of electrons as a dash that represents the bond. So I call the Lewis theory of bonding the connect the dots method. You are connecting dots. In order to share a pair of electrons, each atom that comes into the bond must have something to share. You don't show up at a potluck without bringing a dish, because you got to share something to get something. Otherwise, people will glare at you. So each hydrogen here brings an electron to share, and they share the pair of electrons. Therefore, you can make a bond wherever you have 1 electron sitting by itself. Let's look at another compound. Let's look at, not compound, this is still an element. Let's look at F2. Fluorine is in group 7, so he has 7 electrons in his valence shell. How many electrons does he want in his valence shell? He wants 8. That's why it's called the octet rule. Oct meaning 8. The octet rule says that atoms will lose or gain, that's for ionic bonding, or share, there's our covalent bonding, so that they are isoelectronic with the noble gases, which means for anything other than those trying to look like helium, they need 8 valence electrons. So that's why it's called the octet rule. So this fluorine has 7. That fluorine also has 7. I've got 1 electron sitting by itself here, available to be shared. I've got 1 electron over here, sitting by itself, available to be shared. So connect the dots says I can connect from any single electron to another single electron. Help if it would stop making those horizontal lines. Whoop, like that. Ha. If I go fast, it won't know what I just did. So connect the dots. Connect from one single dot to another single dot. That's going to also tell us how many bonds an atom can make. If I'm looking at fluorine, it's only got 1 dot that is by itself that is not already paired up. Therefore, it can only make 1 bond. Compared to oxygen, oxygen's in group 6. Therefore, it should have 6 dots. 1, 2, 3, 4, 5, 6. How many bonds can oxygen make then? 2. Good. It can make a bond right there, and it can make a bond right there. So oxygen can make 2 bonds, while fluorine can only make 1. Hydrogen can make how many? 1, because it's got 1 dot. So it can make 1 dot, or 1 bond. Boron. How many dots would be around boron? 3. So how many bonds can boron make? 3 bonds. So this is the basic idea of how many bonds can you make, and then you're just going to connect the dots. So these are called Lewis structures. Let's see here, we have water. If I wanted to make the structure for water, each hydrogen has 1 dot, so it can make 1 bond. And the oxygen in the center has 6 dots, so it can make 1 bond. So here's our structure after we make the lines. So electrons, unless there's an exception that we'll talk about towards the end of the chapter, are always going to be moving in 2. It'll either be 2 electrons sitting by themselves on an atom. These are called lone pairs. Lone pairs are a pair of electrons that belong to just one atom. They are not being shared. So in that example, oxygen would have 2 lone pairs, 2 pairs of electrons sitting by itself that just belong to oxygen. He's not sharing them with the hydrogens. Versus the bonding pairs are those that are actually in the bond being shared. So these are the bonding pairs. Are being shared. So if they can manage it, they're going to share electrons so that they all have an octet. And this works best for elements in the second period. So we're not going to worry about the metals because remember metals, according to chapter 2, preferred ionic bonds. So when we talk about the second period, we're really talking about boron all the way through fluorine, neon's a noble gas, so he doesn't really like to bond. When we get to the third period, then we've got some exceptions that we can see they'll do. But for the most part, they're still going to try and follow the octet rule. We'll talk later about what happens when third period or below does not follow the octet rule. All right. So single bond is when a single pair of electrons are being shared. We can also have a double bond or a triple bond. So let's, for example, look at our oxygen atom. What's the natural elemental state for oxygen? Oh, what? O2. O2, good. It's one of the diatomics. So let's figure out how the O2 molecule comes about. I have 2 oxygen atoms. Each one of them have 6 dots because it's in group 6. So each one of them can make how many bonds? 2. So if they're bonding with each other, I'm going to draw how many lines between them? 2. So single electron to single electron, single electron to single electron. Let's make it a little bit prettier. I have 2 bonds between the oxygens, and each oxygen also still has 2 lone pairs. So I'll just draw them over here, like that. So that is the O2 molecule, and this is what we would call a double bond because it is sharing 2 pairs of electrons. So it is a double bond. So here's 2 different molecules that have double bonds. Carbon dioxide has double bond between the carbons and the oxygens. While here's ethene, not ethane, that has 2 carbons double bonded to each other. By the way, if we draw the Lewis dot structure for carbon, how many dots will be around it? 4. 1, 2, 3, 4. So how many bonds does carbon need? 4, which is the maximum number of bonds you can have without breaking any octet rule things. It's 4 bonds. That's why carbon is such a good central atom, and it works so great is because it is small, light, reactive, and can make 4 bonds, so it can make nice big structures, such as we would need for, say, organic molecules, which is why carbon is the backbone of organic chemistry, because it's the backbone of all those bigger organic molecules that we have, that we need for life, because it has those 4 bonds. So general rule for carbon is carbon should always have 4 lines coming off of it. So in both of these structures you can count there are 4 lines coming off of each carbon. You can also have something called a triple bond. So a classic example of a triple bond is the N2 molecule. So nitrogen, how many dots are around nitrogen? 5. 1, 2, 3, 4, 5. Just like oxygen and all of the other halogens, nitrogen exists as a diatomic in its elemental form, so that's N2. So draw another nitrogen here. How many bonds can nitrogen make? 3. 1, 2, 3, or N triple bonded to another N with they still have each have 1 lone pair. You can also do this between 2 carbons. So carbon triple bonded to another carbon, and then each one of them still has hydrogen on the end. So this is ethine. No, that's acetylene, sorry. I misspoke. Acetylene. What do we use acetylene for? Any welders in here? Acetylene torches. Very, very hot torches used for welding things. All right. So that's a triple bond. There is technically a quadruple bond you can have, but it is very, very unstable, so it wouldn't really exist for very long. So 2 carbons stuck together to make a quadruple bond wouldn't really be stable. It would pretty quickly break apart. All right. Bond length. When we were talking about ionic bonds, to find the bond length, it was just adding up the ionic radius of the 2 ions, because we were assuming that there really wasn't any overlap between it. It was just the 2 ions stuck together. With the covalent bond, because they are sharing pairs of electrons, their electron clouds are going to overlap. So what we ended up with here is going to be this overlap space. Switch color there. There. So here's the N2 molecule versus the carbon monoxide molecules. So this overlap space means that the radius, we can't just add the radius of 2 nitrogen atoms. We have to measure directly what the bond length is. So in the case of N2, it has a bond length of 1.1 angstroms. In the case of carbon monoxide here, it's going to be 1.13 angstroms. So here's a table that shows on table 8.3, page 336, shows for different compounds what their covalent bond length is. So I wanted to point out what happens as you go from single, double to triple bonds of the same elements. So let's look at carbon to oxygen. CO, CO, CO. So going from a single, double to triple bond, what happens to my bond length? Is it getting bigger or smaller? It's getting decreasing. The reason is because when you go from single to double to triple, you're sharing more electrons, therefore you're overlapping more. If you're overlapping more, you're getting what? Closer or farther together? Closer, right? The more you share, the closer you get. A lesson I keep on trying to drill into my kids. And they're like, but I don't want to be closer to my brother. I don't want to share with him. We can see the same thing happening down here with nitrogen. Single to double to triple, the radius is getting smaller and smaller and smaller. You can't really compare a single bond to a double bond with different elements then, because you also have to play the different radiuses. So we're really just looking at between the same 2 elements what happens when you go to single to double to triple. Also, as you go from single, double to triple, what do you think happens to the strength of these bonds? Is I'm sharing 1 pair versus 2 pairs versus 3 pairs. Which one do you think has the strongest bond? 3 has the strongest bond. Okay. So the old adage, if you have 1 stick and you break it, it's easy. But if you put 3 sticks together, is it easier or harder to break? Much harder to break, so we need to stick together, right? Same idea here. If I'm sharing 1 pair of electrons, I only have to break 1 bond. If I'm sharing 3 pairs of electrons, that's 3 bonds to break, takes more energy. Therefore, triple bonds are stronger than double bonds, which are stronger than single bonds. All right. So a general idea of the properties of ionic bonds versus covalent bonds. We've already talked about what's different there at the atomic level. Now let's talk about what's different about their physical properties. So there's 2 different kinds of forces at play here. There's intramolecular. So intra means within the molecule. So for a covalent molecule, the intramolecular force would be the covalent bond. Versus intermolecular. Intermolecular forces are those between 2 separate molecules. So if I had, for example, water, the intramolecular force would be those covalent bonds. The intermolecular force would mean what is the force between 2 different water molecules. That would be an intermolecular force. So the biggest difference in physical properties between ionic and covalent compounds are the melting and boiling points. Ionic compounds, such as salt, compared to covalent compounds versus water, Which one has a higher melting point? Ionic compounds or covalent? What's the melting point for water? At what temperature does water melt? In Celsius. 0 degrees Celsius. At 0 degrees Celsius, it goes from solid ice to liquid, right? At what temperature does, say, table salt melt? You don't have to know off the top of your head, but do we know, is it higher or lower than water? Much, much higher. At room temperature, salt is definitely a solid, and I can take that salt and I can put it on my kitchen stove and I can heat it all day and it probably won't be hot enough to melt it. Very, very high. Ionic compounds have very, very high melting points. That's because in order to melt, once you melt, you have that freedom of movement. Ionic compounds have to break their ionic bonds so that those ions can start sliding past each other. To go in the gas phase, or boil, even higher, because now they have to completely break apart. Whereas with water molecules, when water melts or even vaporizes, did it break its covalent bonds? Or is it still H2O? It's still H2O. The only thing it broke was not the intramolecular forces, but the intermolecular forces. It broke the forces between different water molecules. Intermolecular forces are much, much weaker than intramolecular forces. So the reason why molecular compounds, even though covalent bonds are stronger, covalent compounds have lower melting and boiling points because they don't have to break their bonds in order to melt or boil. They just have to pull the molecules apart, which is much, much easier. General properties. So this is just comparing two common compounds, ionic compound being our table salt sodium chloride, and our molecular compound is carbon tetrachloride, CCl4. And just showing you at room temperature, carbon tetrachloride is a colorless liquid with a melting point of negative 23 degrees Celsius. And then it will boil to only 76.5 degrees Celsius, so it boils before water would. And just some general ideas about ionic versus covalent. All right. Any questions about ionic versus covalent bonds and the very basic Lewis-Strauss structures? All right. Next section we're going to talk about is electronegativity and the idea of polarity. All right, so let me leave that up so I have some space to draw. So far we've talked about where over here we have covalent bonding where the electrons are shared. Covalent bonding, electrons are shared. And over here on the opposite side we have ionic bonding, where electrons are transferred. So it makes it look at first what we've done so far, and certainly what we talked about in Chapter 2, where we're like, if it has a metal or non-metal, it's ionic. If it's non-metals, it's covalent. It makes it sound like it's a black and white picture. But the truth is that this is a spectrum all the way across. We're purely covalent, purely means that the electrons are shared equally. And over here, purely ionic bonding is the electrons are completely transferred. But the truth is the majority of bonds exist somewhere in between here, somewhere along this area, and that is where the electrons are being shared, but they're not being shared equally. One of the atoms in the bond is going to hog the electrons more than the other ones. So this is the unequal sharing. Unequal sharing ends up looking somewhat between a covalent bond where they were shared and a little bit like an ionic bond where we got some charges because the electron was kind of staying on one side. This is called polar bonds. It is a type of covalent bond, polar covalent. Oh well. Polar covalent bond is where the electrons are unequally shared. So they're a little bit transferred, not completely, like an ionic bond, but they're a little bit transferred. They hang out more on one side than the other. That is a polar covalent bond. So the classic example of that would be HF. HF is probably one of the most polar bonds we have. I mean, it's definitely covalent. Hydrogen and fluorine, both nonmetals. So it's a covalent bond, it's a molecule. But who do you think hogs the electrons more, fluorine or hydrogen? Fluorine. So that means that the fluorine is going to have the electrons more of the time, so he's going to be a little bit negative, while hydrogen is going to be a little bit positive. He didn't completely give up his electron, but because that electron is spending more time away from him, he's going to feel a little bit positive. He's going to feel a little bit like he lost an electron. So that's the idea of polar bonds. So these are electron density maps, and this image is figure 8.8 on page 337 that shows three classic examples. So a classic example of something that would be purely covalent would be a homonuclear diatomic. So homonuclear meaning the two atoms are the same, such as H2. Electron density maps show the regions that are rich in electrons, or in other words, the electrons spend the most time, in red, and the regions that are electron deficient, or the electrons don't go there very often, as blue. So in the H2 molecule, and yes, there are two atoms here, they're just overlapping a lot. The electrons are spending most of their time in the region that is shared between the two atoms. So that is very equal sharing. Homonuclears are always going to be equal sharing because neither one of them have the strength to hog the electron from the other because they're equal. They're the same atom, or the same element. Over here, we have the HF molecule. So here's the fluorine side versus the hydrogen side over here. We still are covalent. We still have lots of overlap here, but the electrons are over here more of the time. They're over on the fluorine side most of the time. So fluorine's going to end up being red, while hydrogen's going to end up being blue. Here we have sodium fluoride, which is a classic example of an ionic compound. So ionic compounds, up till now, we said, okay, the electrons are completely transferred, so there shouldn't be any overlap. Does it look like there's any overlap there? Not as much as the covalent, but it does look like there's some overlap here. So here's our sodium, and here is our fluorine. Yeah, it looks like there's a little bit of overlap between there. Not a lot, but there is technically overlap. So ionic compounds, none of our ionic compounds are really what we would call 100% ionic. There's still going to be a little bit of overlap, which means there's a little bit of sharing. But as you can see by the red region, the fluorine side is going to get the electron the most of the time, which makes sense because as an ionic compound, the sodium would be positive and the fluorine would be negative because the electron was transferred from the sodium to the fluorine. So, looking at this polar covalent bond, this symbol right here versus here. An ionic bond, we're familiar. We have a positive cation and a negative anion. But here in this polar, we have the positive and negative with this little symbol in front of it. That little symbol is a lowercase delta, and that's going to mean partial. So I do have some charge transfer, but not a complete electron's worth. Over here, +1 and -1 represented whole electrons. If it's +2, that means it lost 2 electrons. If it's -2, it means it gained 2 electrons. But partial means that the electron was maybe only half transferred. So maybe it's an only +0.5 or -0.5. Maybe it's only a quarter, +1/4 or -1/4. But it's a fractional amount of an electron rather than an entire electron getting transferred there. So that's a polar covalent bond. So how do we tell who's going to hog it? Well, with HF, we pretty quickly said, oh, it's definitely going to be fluorine. Fluorine is definitely going to hog the electrons, whereas hydrogen is going to give it up. But the way that we tell that is by the concept of electronegativity. Electronegativity is an element's strength of pulling electrons towards itself. The more electronegative an element is, the more strongly it can pull electrons towards itself. Electronegativity increases as you go across a period and decreases as you go down a family. Therefore, the highest electronegativity will be all the way to the far right and all the way to the top. Therefore, fluorine is our most electronegative element. We're not worrying about the noble gases because they don't want more electrons anyways. So fluorine is our most electronegative element, whereas down here on the opposite end of the spectrum, these metals are going to have very low electronegativity. So they're not very good at pulling electrons towards themselves. They'd rather give it away. So
oxygen would be pretty high as well?
Yep. So this table, which is figure 8.9, page 338, gives you our relative electronegativity values. These do not have units. These are just relative numbers. The bigger the number, the more electronegative you are. So fluorine here is our most electronegative element, and 4.0 is his highest electronegativity. Oxygen right next to him, 3.5, still pretty electronegative, but not quite as electronegative as oxygen. Chlorine down here, 3.0, so still pretty electronegative, but going down the family, as you can see, it's going to go down. It's going to decrease. Over here, metals. Metals tend to have very small electronegativities. Again, they're not very good at pulling electrons towards themselves. They're better at giving up their electronegativities. Hydrogen. Hydrogen has a relatively low electronegativity for a nonmetal, although it is not the lowest electronegativity on here because the metals have lower electronegativities. So it's technically a nonmetal, so 2.1 is its electronegativity value, but it's still pretty low compared to most of the other nonmetals, certainly much lower than hydrogen. So in a bond that is polar, the electrons will go towards the more electronegative element, and therefore that one will become partially negative. So how do we know how to categorize things? That this whole thing is a spectrum from purely covalent to purely ionic. How are we going to break down these categories? That's just showing you the trend as you go across the period. It increases, etc. So here are the breakdowns. A bond between atoms whose electronegativities are less than 0.5, so they're really close in electronegativities, 0.4 or less is the difference, would be purely covalent or nonpolar. Whereas if you are 2 or greater, you're going to be ionic. Anything in between, so in the range of 0.5 to 2.0 is in the range in between, is going to be polar covalent. So back to our idea of the spectrum from purely covalent or nonpolar on one end to purely ionic on the other end. The range from 0.5 difference in electronegativities up to, but not including, 2.0, this whole range is going to be the polar range. So let's look at these. Classify the following bonds as nonpolar, polar, or ionic, given these values from that table we just saw. So ClF, the bond between chlorine and fluorine. So chlorine has an electronegativity value of 3.0, and fluorine is 4.0. So what is the difference in their electronegativities? 1. So 1.0 difference is in what range? Good, polar covalent. So that one will be polar. All right. Cesium versus bromine. So cesium is 0.7 and bromine is 2.8. So that's the difference of what? 2.1. So that's in what range? Ionic. Good. 2 or greater is ionic, so that's definitely ionic. The last one, the carbon-carbon double bond in C2H4. So there's our C2H4, 4 hydrogens like that, double bond carbon, there. So carbon has a value of 2.5, but we're not comparing it to the hydrogens, we're comparing it to the other carbon, who is also 2.5. So what's the difference? 0. So what kind of bond is that? Nonpolar. Good. Yeah. By the way, carbon to the hydrogen had a value of 2.1. What's the difference between those two? 0.4. So the bond between carbon and hydrogen is also nonpolar. So this is just generally categorizing it. Next time we will talk about within that polar range how to quantify how polar it is, or how to calculate how polar it is.